So we will continue the discussion on Lagrange multipliers. In the last class we have seen the test for maxima or minima. So we went through a very tricky mathematical derivation where we looked at the second order terms in a Taylor series expansion, and we established the conditions required for a minimum, and I also told you that there are conditions for maximum. There are also conditions for a saddle point or an inflection point. In the first half of today's class we will solve one or two problems to reinforce our concepts, whatever we have learned with regard to test for maximum or minimum. To make matter simple, I am choosing some of the problems which you already worked out in the previous classes. Okay, let us consider this problem. What will be the problem number? $27. Okay. So we are revisiting an earlier problem. Okay, the problem is like this: minimize y is equal to x1 x2, y is a function of x1 x2 equal to x1 minus 8 whole square plus x2 minus 6 whole square using Lagrange multipliers. Check for minimum using the Hessian. So this is an unconstrained optimization problem. We already solved it. Dou y by dou x1 equal to 0, dou y by dou x2 equal to 0. It is pretty straightforward, right? You get the solution. Basically circle. Okay, the right side y is actually the r squared, the square of the radius. So you know that the minimum occurs at 8 and 6 when x1 equal to 8 and x2 equal to 6, right, which corresponds to a point, alright. Now please evaluate the second order derivatives, get the a11, a12, a21 and so on, and then compare it with the conditions which I gave in the last class, and then get yourself convinced that the stationary point you have obtained is indeed a minimum. Alright, I will give you 5 minutes. So let me just get the solution for you. Alright, so graphical depiction of the objective function. Now the second order derivatives are pretty straightforward. Is equal to 2 0. Okay. the solution is a minimum, pretty straightforward. Okay. See, for many problems the minimum is not so obvious because there are far too many variables, you do not know how it is behaving and all that. Therefore, it is good for us to have a condition like this which is very rigorous, mathematical and systematic. Only thing is, if you have more number of variables, getting the determinant of the Hessian and all that is going to be extremely painful. Okay, but there is no other way. Is it so hopeless that there is no other way? I keep telling, in most engineering problems it is reasonably well known whether we are, say, heading towards a maximum or minimum, but for mathematical exactness, okay, if you want to be rigorously mathematically establish it is a minimum or maximum, all these are required. For most engineering problems it is obvious whether the stationary point is a maximum or a minimum. Yeah.
For 3 variables, what will the Hessian look like?
It will be 3 by 3.
3 by 3 and the first will be a11, a12, a12.
Dou squared y by dou x1 squared, dou squared y by dou x1 dou x3. Okay.
a11, a12, a13.
A11, A12, A13, A21, A22, A23, A31, A32, A33. Suppose you have 10 variable problem, you will be sunk. You have to write a separate program for calculating the Hessian. Already there is a pain in solving the Lagrange multiplier equations and all that. Okay, fine. So this we will solve one more problem. Is this clear? So for a simple case where the objective function is actually circle, the circle of radius x1 minus 8 whole square plus x2 minus 6 whole square root of, that is the radius. So the solution is like this. So problem number 28. Please revisit the cylindrical solar water heater storage problem. Okay, minimize. AR squared H is no. Okay. Pi r squared H equal to 4. Revisit this problem and treat it as a constraint optimization problem. Do not try to make it constraint and make it a single variable optimization problem. Alright. So the equations are pretty simple. This can be, call it phi or v, does not matter. Yeah, what was the R plus? 0.866. What was the answer, Deepak? 0.866. So R plus So the problem starts now. Establish that the solution is a minimum. Needless to say, establish that the solution is a minimum using the Hessian. you can convert it into one variable problem and prove that the second derivative is greater than 0, which we did in one of the earlier classes. Now we will formally use the Hessian. This solution, everybody has the solution, right? We already solved it in one of the earlier classes. So dou A by dou R is four pi, okay. Zero. Therefore, where? Yeah, yeah. What are you getting now? Wait. Dou A by dou R is, I made a mistake here. 2 pi h. That's why. Okay. 2 pi h.
The last one is 2 pi.
Just hang on.
A21.
Yes. 2 pi. Fine. Fine. So d is 4 pi. Zero, huh? Correct? This is 0, right? Then is it? D is negative. Giving trouble. Huh? What about the A11? Negative? A11 is? So what was the condition for us? Huh?
D is negative. A22 is 0. Yeah, so
Yeah, here A22 is 0. There is a problem because we don't have, it doesn't vary with the variables. Anyway, according to whatever we have, according to the rules, it is inconclusive, right? Or what is it? It is inconclusive. D has to be positive or negative. And what did you say?
Hessian is equal to 0.
No. What did we say?
We said
A11
D is
and
0
A22
is not
has to be greater
conjugate.
than 0 and then
Yeah, A11 is A11
and A22 both have to be positive.
See, when I said A11 is greater than 0, why? So special treatment only for A11. Automatically implies A22. If any of these dou squared y by dou r squared or dou squared by dou h squared, any of these things become 0, then already the second derivative is becoming 0 of a particular this thing, right? Then automatically it is a, what does it mean? It becomes inconclusive. Okay. So Senthil, what happens is if d is less than 0, provided all the other, provided none of this is 0, then in whatever you are saying is fine, that it is a saddle point or all this. But now instead of starting the test with A11, we could have started the test with A22 also. When you say that, then when I said that if A11 or A22 is 0, then it is inconclusive. So we have to say that it is inconclusive. But however, However, if you convert it to a single variable problem, we establish that this is indeed a minimum, or you can exhaustively search, you can do all combinations of R and H, write a computer program, and with the precision of 0.0001 10 to the power of minus 5 millimeter, whatever, minus 4 meter, minus 5 meter, you will still not be able to get something which is having a area less than this. Okay, so we should not get carried away by the Hessian test and all that. I mean, sometimes what common sense tells you, the Hessian may not tell. Okay, here I hope there is no bug here, everything is fine. Okay, now we will solve a practical problem using Lagrange multiplier method before we close for this class. Then at 2 o'clock I will teach you the very important Kuhn-Tucker conditions, I mean wherein we will be able to solve Lagrange multiplier, use the Lagrange multiplier method for problems with inequality constraints also. Okay, so now we will go to problem number 29. If you see the other problem also, y equal to 4x1 plus 3x2, we solved, right, y equal to 4x1 plus 3x2 subject to that one also. If you look at the second derivative, it will all be it will all, when the solution is so obvious, if you overdo by doing the Hessian and all that, it will confuse you. Okay, everything will be 0, but it is so obvious the solution. Alright. So, but if you have a function like e to the power of x, e to the power of 3x, or sin x and sin hx, or then it will keep on, you can keep on differentiating, right. But if you have x squared, you can do only one step, 2x, and then the other next step you are sunk. E to the power of x, you can keep on going, right. So, it depends on the nature of the function, right. Fine. 29, is it 29? I will also put it up on the computer screen, but basically we have a problem like this. This is a problem from fluid mechanics. Okay, flow in a pipe network. Okay, we are trying to optimize it using Lagrange multipliers. Is it okay? Where should this come? It does not matter, okay. So, I have a circular duct whose diameter is varying. It is not varying with x as a function or something, I mean it has got discrete three values d1, d2, d3. Air is flowing in. So, this m1 is 4 kgs per second. Here I am pulling out 1.5 kg per second. Here I am pulling out another 1.5 kg per second. So, here under steady state m4 has to be 1 kilogram per second, right. So, it is basically air, rho is equal to 1.18 kilogram per meter cube. All right. The friction factor for turbulent flow is given by the kinematic viscosity of air is given to be 15 10 to the power of minus 6 Which both sides? No, I have not drawn properly. No, it has to be equal, right? Now this is tricky. Now again I am pulling it out. Okay, let us draw without the, then I will pull out. Is it okay? Now you say, here you are taking it out. Is there a mistake here? It's all right. It's okay or? Yeah. Okay, the circular duct, right? D1, D2, D3. Friction factor is given like this. Mass flow rates are given. Total area available, sheet metal area, (120 meter square). Total sheet metal area is 120 meter square. Leave the sheet metal required for pulling out this. Okay, these are not important. And then this is 6 meters. This is not to scale. This figure is not to scale. This is 8 meters, and this 10 meters. That is L1 is 6 meters, L2 is 8 meters, L3 is 10 meters. The lengths are given, the mass flow rates are given, the properties of air are given, right, and the formula for friction factor is also given. The total sheet metal area is also given. So what is the problem? Find the diameter such that the total pressure drop is minimized. It is a standard problem in fluid mechanics. Okay, what is the problem? Objective. Needless to say, you have to use a Lagrange multiplier method. Do not get confused. I am talking. We are still talking about incompressible flow. Do not treat it as total pressure drop. Okay, it is a total pressure drop. I am not talking about stagnation pressure. Can I have the screen now? Yeah, you can start working. This problem will come up on the screen also, just in case. I also want to check whether I made any mistakes on the board. The first line is determine the diameters D1, D2 and D3 in the circular duct shown below. So here it is given clearly 6 meters, 8 meters, 10 meters, 4, 1.5, 1.5, 1, D1, D2, D3. Viscosity is given. Set up the problem. First calculate the delta P1, delta P2, delta P3 for each of the sections. Add delta P1, all the three are in series, right. Total pressure drop is delta P1 plus delta P2 plus delta P3. That will be the objective function that has to be minimized. The constraint, I have given a constraint in terms of the sheet metal area, the total area. I will take attendance and then I will start working out. If everybody is through with this, we will take it off so that we can use the blackboard. Okay, so the objective function is subject to pi d 2 pi r
6 pi d1 plus 8 pi 6 pi d1.
yeah. Okay. psi d1 L1 okay. Now what is delta P1? So delta P1 correct, delta P2 what expansion another thing.
Use the kinetic like b square, b2 square minus b1.
You can neglect all those. Okay. So we can, after finishing the solution, we can check if we want whether really contributing or whether it is a frictional losses, whether the FLV squared by 2 GD is much more substantial than the kinetic head loss, right. Now are there additional relations which are available? Are there additional relations available to us? Yes, sure. M1 okay. So you can substitute for rho 1.18, M1 is 4, M2 is 2.5, 1, good. So please tell me the relationship between okay d1 squared v1 equal to we will do some simplification. Can you tell me? Vinay, can you just tell me the value? Is d1 squared v1 equal to 4 into 4 divided by 1.18? You don't do the steps. Sureka, you have it?
4.318.
Good, 4.32. Then d squared v2.
2.7.
2.7, okay, fine. d3 squared v3 huh? 1.08, fine. Now we will work out for delta P1. The same logic is applicable for delta P2 and delta P3, though the value of the L, D, everything is changing, right. So let us see. Now we are able to see that there is considerable effort in formulating the optimization problem. This is what is normally encountered in engineering. Nobody, suppose you are doing a project, nobody will tell you maximize y is equal to x1 minus 8 whole square, minimize y is equal to x1 minus 8 whole square. That is okay for teaching and that is okay for if you are attending a mathematics course, but in engineering the problem will start like this. You have to use your knowledge of fluid mechanics or thermodynamics or power plant or heat transfer or stress analysis or whatever. Then you will come to a stage and then hopefully after we have formulated it is in a form which is amenable to solution by Lagrangian multiplier. But since I have already solved, you can believe that this can be solved by Lagrange multiplier. Sometimes you think it can be solved by some method, after you formulate it you realize that it does not work, or even after, sometimes even after you formulate it you feel it will work and finally when you write the program it does not work. So optimization is not so straightforward in real life problems, right. Here you can see that there is considerable labor in formulating the problem, okay, though we are not using any advanced concepts, okay, there is a lot of algebraic manipulations involved in getting the objective function. So you want to develop a network for a big colony, or you are a Chennai Metropolitan Development Authority, you are looking at a piping and this thing, a Chennai Metropolitan Water Supply and Sewerage Board, they are coming up with a new desalination plant, they have earmarked some areas in North Madras for this, it is going to be a lot of work with diameters, this thing, friction factors, and what will be the pressure at the tail end of the pipe from the station to from the works, if you are looking at something which is 15 kilometers 20 kilometers away, and right, something like this we will do. Okay, so delta P1 by 2 rho is there, right, the G got cancelled, right. Okay, so delta P1 okay, I have done several things here. Wherever we got what is that, instead of velocity I have substituted 4.32 by d1 square which I got from here, okay. Instead of friction factor I substituted 0.184 Reynolds number to the power of minus 0.2. The alternative formula for Reynolds number in terms of mass flow rate is 4m by pi mu d1, okay. Now you can see that delta P goes as d the power, this is what is solved for the pipe, and for your assignment 1 d goes as minus 4.8, correct, d goes as minus 4.8, that you should never forget, okay. Then you can assemble all the other things and put it as a constant. Can you tell me, so you know all the other values, m, this is m1, you know m1 L1 rho everything, so delta P1 is equal to huh
982 by d1 power 4.2 plus.
I have the solution, but I don't know whether it is correct, so well, let us see. Uh, 0.971, huh? Okay, does not matter. So 0.971 d the minus, good. Similarly, yeah, I hope all of you are able to follow these arguments, right. So you have to substitute and it's just bulwark here, right. So similarly delta P2, where?
The bracket.
Sure. Yeah. You are able to see from there? You require a periscope. Vipin, I gave you attendance, don't worry. You can't see anywhere, right? You require a periscope. Huh? There will be transmission and distribution losses. Okay, so similarly delta P2 equal to, Vikram, you are very sleepy today. What happened? The camera caught you. Delta P2?
0.562.
Good, 0.564 or whatever. Point 180. 135. Is that right? No, all my answers are wrong. Okay, so point 135. You got it? Anand, 0.135. Oh, d3, okay. So you can expect a problem of this difficulty level in quiz 2, right? Not x1 minus 8 whole square plus x2 minus 6 whole square. To spice it up, we can have problems where UA LMTD is equal to MCP delta T and you have to differentiate log and all, correct? Therefore, y min y is equal to yeah. Now this is 0.971. Subject to six d1 plus 8 d2 plus 10 d3 is equal to 120 by pi. 3 d1 plus 4 d2 plus 10 d3 what happened? Oh, so what is this anyway? 19 point 18 point, how much is it? Good. We have not solved the problem, now we have formulated the problem. Yeah.
This area, you're not taking the granular this thing between the.
Yeah, we'll leave all that. I am making some approximation here to make the problem tractable. Okay. You can write a program and solve it if you want. I will look at it. Okay, then as he said, we have not considered the other kinetic losses and all that, kinetic energy losses. Fine. Now we have to use the Lagrange multiplier method. Okay. So this is phi, huh? Correct? All right, lambda any problem? Huh? Wait. So lambda can be negative, no? Lambda is unrestricted in sign. You assume lambda is negative, therefore the root is possible and all that. Don't worry about it. Actually, this is how many unknowns are there?
4 unknowns.
4 unknowns. But I mean, at first sight you will feel, oh, it's not solvable. But actually, the resulting Lagrange multiplier equations are pretty straightforward, very simple. You can solve, right? So shall we do that? See, there is a problem. Root of minus something is coming, no? That doesn't matter. Lambda is minus we can take, or we can take this whole thing as d by d1 plus lambda. I mean, lambda is unrestricted in sign. We saw that the only requirement was del y and del phi must be collinear. Okay. I asked this question in 2009 EndSem. So it is not coming for quiz 2 and EndSem, okay. Okay, phi equal to 0. Now what is it? What is dy by d1? Rohit, wake up, Sid. Dou y by dou d1 is 0.971 minus 4.8 d1 minus 5.8 minus lambda, oh this is so nice, into 6 into 3 4 5, right. Okay, 0.564 okay. So d1 is, or lambda is, or d1 is in terms of lambda. We put d1 in terms of lambda, d2 in terms of lambda, d3 in terms of lambda, and then substitute for d1 d2 d3 here, you are home. Okay, so d1 equal to, please tell me Vikram, d1 1 point lambda raised to
minus 1 by 5.
0.172. D2, yeah, D2, how much is it? 5.64 into 4.8 divided by 4, 1 over that. .5 lambda to the power of minus 0.172, right. D3, huh? 7.7 lambda to the power of minus okay. Therefore, lambda should be negative, right. You have already made the correction. How much is lambda? Huh? How can d1 be negative? You adjust lambda.
L2 plus lambda.
Some adjustment is there. Is this correct, Deepak? Don't lead me into the wrong path. What is lambda finally? Why is everybody blinking? Lambda is how much? Point naught something. 0.0286. Good. Lambda is from this, based on this. Okay. Yeah, D1, D2, D3. Abhishek, you didn't get? Yeah, you can substitute there. Kaustubh, yeah, what is D1? 3.13. D2?
2.76.
D2 is how much?
2.76.
Huh?
2.76.
D3? Large numbers.
Sir, how can that be? That is 1.5. Sir, first one will be wrong.
Which one?
D1 D2 actually greater than D1.
Lambda to the power of minus 0.1. So lambda is less than 1.
Both are common.
D1
No.
should be greater than
D1 should be greater than D2, should be greater than D3. Alright. What is D3?
D1 should be greater.
0.93. So D2 is 0.93. D3
What is D1 finally?
So the coefficients over there for besides
These are not correct.
1.07 is the first one. The second one 0.93.
Ah, okay. Point?
68.
Yeah, so there is a mistake here. Yeah, now tell me D1, D2, D3. Vikram, now you will be happy. Why are you struggling? Huh? Okay, why are you struggling? 1.97? 1 point? Third one?
The last one has 1.279.
Okay. Okay, the way it is, the way the values are given, D1 has to be greater than D2 and should be greater than D3. But the way the figure has been given in the problem, I can now say that I gave that figure to mislead you or whatever. But after I gave the question, I realized that D1 was greater than D2, but I thought I'll leave it. Okay? So don't get carried away by that is just a depiction. D1 is different from D2, it could be different from D3. So we can complicate this by having several streams which are coming in or going out. We can have several D1, D2, D3 up to Dn and so on. Simple fluid mechanics Darcy-Weisbach equation FLV squared by 2GT can lead to so much. Suppose apart from fluid flow we have heat transfer also, there is a heat exchanger, there is a hot fluid, cold fluid, so several combinations are possible. How did the coefficients? Arithmetical error. No, because I have, of course I made a mistake in delta P3. I got values which are close to this. For my diameters were 1.95, 1.69 and 1.336. I just worked out before coming to the class. It's basically that minus 5.8 and all that's all tricky. Just work out the algebra patiently. It can't lead to, lambda should be very small. Lambda must be negative, isn't it? No, you adjusted here. Okay.